polarized light and ordinary light, and also how to produce polarized light. These are the things that we'll be discussing today. Now, ordinary light, like here by ordinary light we mean which is unpolarized. For example, the light coming from the sun directly, and if you know can find out the vibrations of the electric field in a particular plane perpendicular to the direction of propagations, then you will find that there is electric field vibrating in all the directions and denoted by star. So it seems to be symmetrical, but yes, it is in the you know plane perpendicular to the direction of propagation. So electric field can vibrate in any directions here, but please remember it has to be perpendicular to the direction of propagation. For example, if the wave is traveling from the screen towards you, then electric field can vibrate in all possible planes of the screen in which you are seeing, either computer or mobile. So ordinary lights are represented by star. Ordinary light, it's not polarized, I'm sorry, this will be ordinary light, this is unpolarized. Ordinary light is not polarized. Ordinary light is represented by star. Okay, so it's not a polarized light, so electric field vibrating in all possible directions perpendicular to the direction of propagation of the light. Now, in case of the plane polarized light, as we told earlier, that vibrations will have along a single line, and that should be perpendicular to the direction of propagation. So, like we were telling that electric field vibrating in a plane, in the xy plane like this, or electric field vibrating along a axis, say x, or vibrating along y. So these are all linearly polarized light. So electric field will be vibrating along a particular line, and that is perpendicular to the direction of propagation. So the light is propagating again perpendicular to this plane, for example. Now, when the plane polarized light has vibrations in the plane of the paper, they are represented by straight arrow. For example, if the vibrations is in the plane of the screen, then it will be designated by a arrow. Or when the vibrations lie in a direction perpendicular to the plane of the paper, they are represented by dot. So it is possible that your directions of the vibration is perpendicular to the plane of your screen or plane of the board, then it will be represented by a dot. Okay, but both has to be perpendicular to the direction of propagation of the light. That is for sure, because for the transverse nature to otherwise transverse nature will not remain valid. So this is the representation of ordinary light and polarized light. Now let us try to understand how to engineer such polarized light, how to produce such polarized light, what are the techniques. Now, so at this stage we have the idea of what polarized light is. So the next step will be to develop an understanding of the technique used to generate it, change it, and in general manipulate it, like how to produce a polarized light, how to change the polarization of that light, and then how to in general, like manipulations of the polarization of the light, how it is possible. So that we will be discussing now. So sometimes question asks that what is a polarizer? So polarizer is an optical device which polarizes the light input into it. So it is a device which polarizes the light, but how it does? So that we will be discussing next. So like for example, recall that one possible representation of unpolarized light is the superposition of two equal amplitude incoherent orthogonally polarized state. Like for example, we are discussing unpolarized light. So this unpolarized light, this can be represented as a superposition of two polarized light, one say in the plane of the screen and another perpendicular to the plane of the screen. So any unpolarized light can be considered to be superposition of two perpendicular component, okay, and they are incoherent mixture. So, and we need an instrument that separate these two components, discard one, passing on the other, that is a linear polarizer. So if you have a unpolarized light which can be assumed to be consist of two components, one say perpendicular component, one horizontal component, and you have a device which discard one component and pass another component, then that light will be polarized in a particular direction. So electric field will be vibrating in a particular direction, so you get a linearly polarized light. And also, we can also produce circular and electrical polarization. But how to do? What are the things we require? You understand that the polarization means there is some want of symmetry in the light. So the technique what we will be using, they must have some property, that material what we will be using, the device what we will be using, they must be able to introduce this asymmetry in the vibrations of the electric field of the incident wave. That is essential. Now we will see that this can be done by utilizing four fundamental physical mechanisms. This process, like introducing asymmetry in the vibrations of the electric field of an electromagnetic wave, can be done by four fundamental physical mechanisms. There is four fundamental physical mechanisms. They are dichroism. Dichroism means selective absorption. So they absorb particular component of polarization of the incident light. So it is called selective absorption. So there are some material which absorbs the light based on the polarization. So it's called the dichroic material, and the phenomenon is called dichroism. So by using the phenomenon of dichroism or selective absorption, by using the phenomenon of reflections, you already have studied Brewster's law in Newton plus 2, that when a light is reflected, it becomes polarized. So we'll be discussing that also today, that by using the phenomena of reflections, you can produce polarized light. And there is another scattering phenomena also can be used to produce polarized light. And another is the birefringence or double refraction. The phenomena of double refraction actually was discovered by Erasmus Bartholinus in the long back, and when he was trying to study some crystals. Actually, polarization was not his job. He was a crystal grower, and he was growing different crystals. And then I'll tell the story other day that like this, that when he was observing his crystals in a afternoon in the sunlight, suddenly found two images of the sun. And then later on he untried he studied this phenomenon and found that this is because of property of birefringence of the material, and the light becomes separated into two polarization components, and so two images of the sun he could see on the crystals, but it happens only in particular direction. So we'll be discussing details later on. So we will remember that there are four fundamental physical mechanisms by which polarized light can be produced. There are four fundamental mechanisms. They are the phenomena of dichroism, phenomena of dichroism or selective absorption, phenomena of reflection, scattering, and birefringence or double refraction. So which I have already told that there should be one underlying property that all these four phenomena will share, which is simply that there must be some form of asymmetry associated with the process. So usually it comes from, it is an anisotropy in the material of the polarizer. Like you use some material to show dichroism, use some material from where the light is reflected, use a material where the scattering of the light takes place, or use a material where there is a double reflection phenomena takes place. So this asymmetry is basically coming from the material. So these are the four fundamental mechanisms, that is dichroism, reflection, scattering, and birefringence. Now let us discuss the law of Malus, which you also do in the lab. So in 1809, more than 200 years before, he discovered this phenomenon experimentally, that when a completely plane polarized light is incident on an analyzer, the intensity of the emergent beam varies the square of the cosine of the angle between the plane of transmission of the analyzer and the polarizer. So you see that this experiment goes like this. Say you have an unpolarized light which consists of the vibrations of the electric field in all possible directions. Then you pass this unpolarized light through a linear polarizer. So whose path axis is like this. Path axis means that this is how to pass the light which are vibrating only along these directions, not other directions. So when this light will pass through this polarizer is using the any of the phenomenon as you have discussed. So and then we get a linearly polarized light. Now when this linearly polarized light pass through analyzer with a path axis which is making angle theta with the axis of the polarizer, then the intensity of the light which will be passing out from the analyzer will depend on square of the cosine of the angle between the axis, path axis of the polarizer and path axis of the analyzer. That's the Malus law. So please remember, in a Malus law, you incident a polarized light to the analyzer, not an unpolarized light. Okay, unpolarized light has to be polarized by the linear polarizer, and then this light is incident on the analyzer. Now the light intensity of the light coming out from the analyzer depends on square of the cosine of the angle between the axis of the polarizer and axis of the analyzer. Now to prove it, let the angle between the two planes of the transmission of the polarizer analyzer is theta as shown, and r the amplitude of the incident plane polarized light. So please mind it, r is the amplitude of the incident plane polarized light, not that of the unpolarized light. Okay, amplitude of the linearly polarized light is designated by r, not that of the unpolarized light. Now r can be resolved into two components. One is along the path axis of the analyzer and perpendicular to the path axis of the analyzer, along AE and along AO. So AE is basically r cos theta and AO is r sin theta. Now as you know that perpendicular component will be absorbed by the analyzer, whereas it will not be allowed to pass through. So parallel component will be freely transmitted through the analyzer. So the light which is passing through the analyzer will have a amplitude r cos theta. So intensity of the light is proportional to r cos theta squared, so that is I0 cos square theta. That is the proportional to the square of the cosine of the angle between the axis of the polarizer and axis of the analyzer. So I0 is the intensity of the completely plane polarized light. Please remember, this is not the intensity of the unpolarized light. Sometimes an examination question asks that let the intensity of the unpolarized light is given, then what will be the intensity of the light coming out? So in case of say you incident here I, then here it will be I by 2, because this is unpolarized light, so on the average it will be I0 by 2. So that will be incident on the analyzer. So please remember that. Now we'll discuss the phenomenon of reflection by which you can produce polarized light. That is Brewster's law. So again in 1881, much later than when Malus law was discovered, that Brewster discovered a phenomenon which you have studied, that when an unpolarized light incident at an interface between two medium, then the reflected light, and when the angle of incidence is equal to a particular angle, then the reflected light become completely polarized in a plane perpendicular to the plane of incidence, and the reflected and refracted light become 90 degree away from each other. That's the Brewster law. So he observed that discovered a simple relation between the angle of incidence at which the maximum polarization occurs and the refractive index of the media. What he observed? He observed that for a particular angle of incidence, which is called the angle of polarization, the reflected light is completely plane polarized, with the plane of vibration perpendicular to the plane of incidence, with the plane of vibration perpendicular to the plane of incidence. So we have a unpolarized light which can be assumed to be consisting of the equal mixture of one horizontal component and one vertical component. So there are two polarization that we have denoted in the figure with the arrow and double arrow and a dot. So that means this is unpolarized light which can be assumed to be consisting of both the polarization component. Now when the light is incident and the angle IP, that is called the angle of polarization, polarizing angle, the reflected light BC is completely polarized in a plane perpendicular to the plane of incidence. So only vertical component is existing here, and under these conditions your reflected and the refracted light are 90 degree away from each other. So this angle is 90 degree, they are 90 degree away from each other. Okay, so this can be easily shown that mu is equal to tan IP by using Snell's law here, sin IP by sin theta p, for example, and then by using the relation between IP and theta, we can show very easily that mu is tan IP. So by doing experiment, you can measure the value of IP and then you can measure the refractive index. So this experiment can be easily done. Like if you have a glass surface, then you know the angle, you can calculate, you know the mu, then you can calculate the angle at which light has to be incident. So this, by using this phenomenon of reflections, we can produce polarized light. Now there is another phenomenon I was telling you that, so we'll discuss this and then we'll stop. So there are certain crystals which called doubly reflecting crystals. There are some crystalline materials which exhibit the property of splitting an incident ray into two reflected rays. Such crystals are called doubly reflecting crystals. And so what are the doubly reflecting crystals, or the crystals which exhibit the phenomena of double reflection? And the phenomena of double reflection, like you incident unpolarized light in certain crystalline material, basically they are called anisotropic material. They are not isotopic. The optical property are direction dependent. When an unpolarized light incident on such anisotropic material, the refracted light become divided into two parts. One, and then experimentally it is found that one light ray is polarized in a plane perpendicular to the plane of incidence, and one is polarized in the plane of incidence. So these two light rays are called ordinary and extraordinary light, and this type of material are called doubly reflecting material, and the phenomena is called double reflection. So there are certain crystals which exhibit the property of splitting an incident ray into two reflected rays, and such crystals are called doubly reflecting crystals. And this phenomenon of splitting an incident ray into two polarized ray, different polarized ray, are called the phenomena of double reflection. Now there are these type of crystals are categorized into two classes. One is called the uniaxial, another biaxial. I was telling you that you incident the ray in such crystals, they will be splitted into two rays. But in all these material, they are anisotropic, but there is one direction. There is one direction exists along which the material is fully symmetrical. So that is called the optic axis of the crystal. So these material also have a direction which is symmetrical. So with respect to that, the crystal looks symmetrical. So if the light ray incident along that direction, even ordinary light, means unpolarized light incident along that direction, it will not be separated into two rays. So in double reflecting crystals, the incident light is splitted into two rays. But if it incident along the optic axis direction of the crystal, then it will not be splitted. So except along the optic axis direction, it will be splitted. But if light incident along the optic axis direction, then it will not be splitted. So there are certain crystalline materials in which there is one axis, such optic axis, they are called uniaxial. But there is another category of material where there are two such direction exist. So they are called biaxial. Okay, so there are two type of material, anisotropic material, one called the uniaxial material, other biaxial. Uniaxial means there is one direction of maximum symmetry. So although these materials are asymmetrical, but along this axis the material looks symmetrical. And also there are other categories of material where there are two such axes. So the material is symmetrical with respect to these two axes. Now in uniaxial crystal, as I told, there is only single direction, no optic axis. So along which two reflected rays are transmitted with the same velocity, because refractive index is the same. So there and the polarizations are different, and these materials has polarization dependent refractive index. So when the light is polarized in the horizontal plane, the refractive index will be NE. When the light is polarized in the vertical plane, the refractive index will be NO, and this value of NE and NO are different in general. So but along the optic axis, these two values are the same. So they travel with the same velocity. Other than that, they travel with different velocity. Out of the two reflected ray, only one follows the ordinary law of reflection. So and that's why it is called ordinary ray, that is vertically polarized light, and horizontally polarized light is called externally polarized light, because that travel little away from the direction. So the example of these crystals, there are many examples. In the earlier days, the people use calcite crystals, calcite and tourmaline, quartz. These are the earlier crystals. Now recently, a lot of new crystalline materials have been discovered by the people, in the current years. I mean that not in the 2000, but maybe in the 1980 or so, like BBO, the beta barium borate, was discovered in 1984, and CGF lithium borate discovered in around 95 or so. So these are some new crystals, and potassium dihydrogen phosphate, these are also have been discovered in the past. So there are some crystalline materials. You remember some examples, may not be many. I don't want to put you trouble to remember so many crystals. So at least 2-3 you remember, like calcite, tourmaline, quartz, BBO, ClBO, beta barium borate, CgM lithium borate, ClBO, and this is KDP, potassium dihydrogen phosphate. These are the uniaxial crystals. And there are certain other crystals which has two directions, as I told, and none of the reflected rays obeys the laws of reflections. So and examples of biaxial crystals are copper sulfate. In biaxial crystals, there are two directions or the two optic axes along which the velocity of the reflected rays are the same. And other than this sentence is not that much meaningful here. So other than the direction of optic axis, the light rays are separated into two rays. Okay, light rays are separated into two rays, and in biaxial crystal is a bit complicated. So I'm just cutting this line so that you don't need to go through it, because it's a bit complicated to understand for you for the time being, because we do not discuss further details. In case of the biaxial crystals, the refractive index behavior is a bit complicated. So anyway, so you just remember that there are certain crystalline material where there are two optic axis directions along which the velocities of the reflected rays are the same, and then the light ray don't get separated. And some common example like urea crystal is a urea you might be knowing, and the copper sulfate also you might be knowing, and cane sugar, mica, these are the examples of biaxial crystals. So there are two optic axis directions. So this is about the doubly reflecting crystal, some introductory discussions, and what is the phenomena of double reflection, that at least you should remember, and what are the uniaxial crystal, what is biaxial crystal. So these are the phenomenon that I wanted to discuss, and then we have one more class we need for the polarization, where we will discuss the phenomena of dichroism, and we will discuss the Polaroid and their applications, and we will solve some problems. So today we'll stop here. So today basically what we have discussed, that we have discussed what is ordinary light, how to represent ordinary light, how to represent a polarized light, and then what is a polarizer, what it does, and how the polarizer works, what are the fundamental mechanisms, and we discuss the phenomena of law of Melas and the phenomena of reflection by which you can produce polarized light, and also we discuss about double refraction phenomena and give some examples. So that's all about today. Now if you have any questions or the doubt you can ask, or we'll give the attendance and then